Okay, welcome back, everybody. We ended our discussion yesterday with a statement that what we were most interested in is dealing with this, what we called an eigenvalue problem. So specifically, we're interpreting this as an eigenvalue problem associated to eigenvalues coming from this symmetric operator A, right? Script A, as I have written here. Okay, so this script A is what's called, or what we're calling a symmetric differential operator, which we defined in terms of those boundary conditions associated with this problem. And this is the problem that we want to find solutions of. And for each individual eigenvalue, a solution is called an eigenfunction of A associated to that eigenvalue. So this is like the key thing we are trying to solve, right? Where x is some unknown function and lambda is some eigenvalue. This is known as an eigenvalue problem, or this is a special example of Sturm-Liouville problem. So this is an eigenvalue problem, or this is a special example, special case of what's called a Sturm-Liouville problem. There are more general things that fall under this umbrella, so you can just think about this as an eigenvalue problem. This is just a special case of a Sturm-Liouville problem. Okay, and so what is it that we are doing, right? So the idea is this is an eigenvalue problem for where a solution x is an eigenfunction of this script A differential operator, which we had defined as minus d squared dx squared, right? So minus the second derivative. So a solution x is an eigenvalue function, or sorry, an eigenfunction of script A associated to an eigenvalue, say lambda. So there's two big assumptions we're going to make. So assume two things. So firstly, assume that there are countably infinitely many solutions to this thing. So there's countably infinitely many eigenfunctions and eigenvalues. So there are countably infinitely many such eigenfunctions and associated eigenvalues labeled as the following. So we have infinitely many of these eigenfunctions we'll label as x sub n of x, and then we'll index these from, say, n equals 1 to infinity. Now, of course, there's nothing, we made that decision, right? There's nothing saying that these have to start at 1, right? They could just as well start at 0. In fact, we'll see examples of where it makes more sense to start this at 0. In fact, you've already seen examples where that's the case. And we index the infinitely many eigenvalues the same way, lambda sub n. Okay, so where each x sub n corresponds to a distinct eigenvalue lambda sub n, right? So x sub n corresponds to a distinct eigenvalue lambda sub n. Okay. The second assumption that we're making, assume that, well, we've forgotten something here, right? So what is our purpose here? Because I'm about to spit out a function that seemingly arises out of nowhere here. So what was our function, or what was our original goal here? Why are we finding these eigenfunctions? So the goal, maybe I'll write it up here. the goal of this solving this equation is to write a given function phi of x on some interval AB as a linear combination of such eigenfunctions. Okay. So the goal is actually to write a given function phi of x defined on an interval as a linear combination of eigenfunctions arising out of this equation. That's why we want to solve this. And so assume that we can achieve that goal, right? So assume that given a function phi of x on our interval a to b, that I can actually write it as a linear combination of those things. So assume that phi of x can actually be written as some linear combination, right, sum from n equals 1 to infinity of a sub n times x sub n, right, for some coefficients a sub n. Right, i.e., assume it is possible to write the given phi of x on a to b as a linear combination of such eigenfunctions. Now again, what is this saying? This is saying that my goal, the thing I set out to do, is actually doable. Okay, so these are the things I'm assuming. Well, let's start with the second assumption that I can actually write it in this way. If I can write it in this way, can I figure out what the coefficients would have to be? Well, yeah, I can actually do this in the same way that I already did this for the Fourier coefficients, right? So it's not surprising to you that where all of this stuff is headed, that you see expressions like this and you say, wait, somehow the Fourier series we've already defined are going to play a role in all this, right? And of course, that's absolutely right. But let's see exactly how they pop up. Okay. So how do I notice this? Yeah. Well, let's first note. So to find a sub n, we aim to make use of orthogonality. What do I mean by orthogonality? Well, in last lecture, right? So in the last lecture, we already showed that the x sub n eigenfunctions, right, as a collection of functions, form an orthogonal set, right, in the sense that, i.e., the inner product of x sub n and x sub m is 0 if n and m are not equal, right? Remember, though, this inner product, of course, is the statement, right, that this integral is 0, right, if n not equal to m, which should, again, ring like recognition bells in your head, right, to get you to see, oh, all right, I've seen things that look like this before. Okay. So we want to use this orthogonality. So how do we do that? Well, let's start out with pairing phi with x sub n. So let's look at this inner product. Well, I assumed that phi can be written as this linear combination, a sub n times x sub n. And so this inner product this satisfies, well, phi is just this sum, so this is the sum from n equals 1 to infinity of a sub n x sub n paired with x sub n. Okay. Now, what is this by definition? So the definition of this inner product, of course, is that this is the integral from a to b of this sum, right, n equals 1 to infinity of a sub n x sub n times x sub n, right, dx. Now, I could have done something slightly different here, right? Like, if you don't like this, I could have immediately written this as, you know, the integral of phi from a to b, like phi of x sub n of x dx. I could have done that and then swapped in what phi is, right? So phi is this thing. This is obviously identical. It's just in case you're confused because a lot of parentheses are showing up here, right? But there's a comma here. So this is the inner product. This is the definition of that inner product, right? So inner product of phi with x sub n is the integral from a to b of phi times x sub n. Okay, all right. And so, so forget about this for a second. Right? This is fine. This is the definition of that thing. But we started here. Okay. So, what do I do here? Well, I'm going to do the thing that I did when I was dealing with Fourier series to begin with, which is I'm going to swap the order of the integral and the sum here. That is something that has to be justified, but it works for a wide class of such things, and so we're in a case where it's actually going to work here. So first of all, let me re-index this because this is a little confusing. N is an index here, right? But N is fixed in this part. So this is a little, I've done something a little wrong here, right? This is not great notation. So why don't I change this N to something else? Why don't I change this N to I, right? That makes it better. And that leads to less confusion. Okay, so there, we'll change our indices to I. That helps a little bit. Okay, well, of course, I can rewrite this term, this x sub n is multiplied by this entire sum. I can distribute that and swap the integral and the sum sign so that this is the integral from I equals 1 to infinity of, or sorry, the sum from I equals 1 to infinity of the integral from a to b of a sub I x sub n dx. Okay. Which is, of course, I can rewrite this now as the sum from I equals 1 to infinity of here. This is the inner product of a sub I x sub I and x sub n. Okay. Well, now what? Well, what term gets picked out here? Again, because of this orthogonality, right, the inner product of x sub n and x sub m is 0 if n and m are not equal, the only term that gets left here is a sub n x sub n x sub n, but by definition of the inner product, I can just pull that a sub n out. So a sub n times the inner product of x sub n with itself. And so I have the statement rewriting this that the inner product of phi with x sub n is equal to a sub n times the inner product of x sub n with itself. but then dividing by this inner product of x sub n with itself, which is non-zero if this thing is non-zero, right? I'm pairing vector with itself here. So this tells me that a sub n is the inner product of phi with x sub n over the inner product of x sub n with itself, which in the language of my thinking of this in terms of that L2 norm, right? This is an inner product of x sub n with itself. So I could also write this as phi paired with x sub n over the length of x sub n squared, if you like. And oh my, those coefficients are given exactly by this. This motivates a definition. Okay, so this motivates the following definition. Okay, consider, so for this definition, this is a definition of what we'll call the general Fourier series of a function. So consider a symmetric boundary condition for the eigenvalue problem as before. I'm just going to say the eigenvalue problem. Maybe I should write it out, right? Okay. Assume there exists countably infinite number of associated eigenfunctions x sub n and eigenvalues lambda sub n, okay, as labeled before. Then the infinite series, which is the sum from n equals 1 to infinity of a sub n times x sub n of x, where a sub n is defined to be the pairing of phi with x sub n divided by x sub n paired with itself, which can be written in terms of integrals as the integral from a to b of phi of x, x sub n of x dx over the integral from a to b of x sub n squared of x dx is called a general Fourier series of phi. For the cases of Dirichlet, Neumann, and periodic boundary conditions, we call the resulting series a classical Fourier series of phi. You're going to see why here in a little bit, right? So very soon you're going to see that if it's a classical Fourier series, that is, if we're in the situation with these boundary conditions that we've had a lot of experience with, right? Dirichlet-Neumann or periodic is our new one we've kind of introduced. We're in the classical Fourier series case, and these eigenfunctions, what do you think they're going to be, right? They're going to be sines and cosines. Okay. And so in our old notation, or not old notation, but in the notation from yesterday that we just introduced yesterday, you can think of this as writing phi as a linear combination, right, of the eigenfunctions. But since these a sub n's have this particular form, this is exactly writing these as a projection, right, onto the eigenfunctions, right? Note, if all of this is true, then phi of x is being written how? Right? Phi is being written as an infinite sum of the projection of phi onto these eigenfunctions x sub n. Okay, in the notation of yesterday. Now, a couple of things I wanted to say before moving on and finishing this all the way out. As I said, we index these from 1 to infinity. There's no reason why we have to do that. We could start at 0. In fact, sometimes it will be very instructive to start at 0 because there will be an associated eigenvalue at 0. Okay, and if lambda sub n depends on n in a way that choosing n equals 0 leads to a 0 eigenvalue, that's going to matter, right? And so so oftentimes we are definitely going to start at 0, and there's nothing wrong with that, right? Indexing beginning at 0 is fine. It doesn't have to be exactly this form. That's the first thing. The other thing is saying that there's like eigenfunction, like a eigenfunction associated to like exactly one eigenfunction associated to a particular eigenvalue is not technically right. So sometimes, for instance, in the case of periodic boundary conditions, it will work out that there will be two linearly independent mutually orthogonal eigenfunctions corresponding to any non-zero eigenvalue. Okay. So those sorts of eigenvalues would be called degenerate, and you can think about how that ties in with all the stuff you did with eigenvalues back in linear algebra, and what it meant for an eigenvalue to be degenerate in that case. Okay, so there's one more thing that kind of tells us that we're in a very, very nice case. Remember, we had the spectral theorem from old linear algebra, right? For like finite dimensional linear algebra. We have a similar thing, at least the consequence of it that we're most interested in is the following, that all eigenvalues so all eigenvalues of the eigenvalue problem x double prime plus lambda x is equal to 0 over functions x of x, where x is in AB, satisfying symmetric boundary conditions, are real. That's big. That's big because typically, right, you can't even say, knowing nothing else, even if I give you like a 2 by 2 matrix, right, you can think of an extremely simple 2 by 2 matrix, right, that only has zeros and ones, minus ones in it. And you can easily come up with an example of a 2 by 2 matrix that has complex eigenvalues, right? So complex eigenvalues are something that are ubiquitous. It's always something you have to deal with. Here, though, we're not going to have to deal with complex eigenvalues here because we're guaranteed that all these are real. This is like a counterpart to our finite dimensional spectral theorem. There's a whole general theory that we could go into here about differential operators in general, but there's just not nearly enough time to go in that direction. That's like a functional analysis type question. If you're interested in that, then by all means, you can have a look at it. You can look into like a more general theory of of like differential operators. But here we're specifically talking about this particular differential operator, you know, minus d squared, right? That's what we're talking about. So for this one, all the eigenvalues, all these associated eigenvalues are real. Okay, and so the big question, right? I want to write out eigenfunctions for each of the typical boundary conditions. So Dirichlet, Neumann, and periodic. And we'll throw mixed in there too. These we'll call these typical or standard, if you like. Okay. So this maybe, in fact, I think it deserves the rest of this page here. I'm going to make big starred statement here. This is of utmost importance to the rest of what we're going to do. Okay, well, let's add some more stars. Maybe up here too. Okay. So this list that I generate here, okay, so writing out these canned eigenfunctions for these boundary conditions is of utmost importance to what is done from here on out with our separation of variables algorithm, because it's basically going to be the thing that we use at each of the solve steps. You'll see what all of that means when I get to actually explicitly writing out the separation of variables algorithm, but for now, just trust me that having these canned eigenfunctions ready to roll at any point is exactly what you want, because it exactly allows you to apply this stuff in the way that you want to. So it allows you, every time you get to a step where you're like, man, I really want to solve this equation, which is one of these eigenvalue problems. Oh, I know the solution. I already know it instantly because I've already solved it. I've already done it here. Okay, so if you like, you can view this as basically this is us coming up with a dictionary that you're just going to refer to, and then, you know, you'll do some other calculations later, but this is basically going to form the backbone of these solutions that we come up with. Okay, so writing out these eigenfunctions for these corresponding boundary conditions is extremely important. All right, let's do the Dirichlet condition first, right? So now I phrased all of this so that we have a generic interval instead, but let's rewrite our interval as 0 to L for L positive. We can do this pretty easily always if we really, really care about it. We could always think about shifting an AB to being this thing. I don't care about that process. So without loss of generality, we can always just assume that we're dealing with an interval that looks like this, okay, for some L greater than 0, right? Just like in our physical situations, we had our bar or our fixed string, right, always fixed in this way. It just makes it easier to describe these things. Okay, and so now let's do the Dirichlet case first. I want to write out eigenfunctions x sub n of x solving the problem, which is my usual eigenvalue problem, x double prime plus lambda x equals 0, with Dirichlet boundary conditions, which is that x of 0 is 0. That's also x of L. Okay. Now, this is an ODE, right? Forget all of this stuff we did before, right? This is an ODE, okay? So this is an ODE, and since this is an ODE, I'm solving it with ODE methods here, right? But there's three cases. Three cases. Now, why can I simplify this to just three cases? Remember what we just said on the previous page. All these eigenvalues related to these problems are real, right? They're real, and of course real numbers satisfy trichotomy, right? They're either positive, 0, or negative, right? Those are the only possibilities for a real number. So my three cases are exactly those. Lambda can be negative, it can be 0, or it can be positive. Let's do the case where it's negative. So first case, lambda is negative, right? Then x double prime is minus lambda x, and if lambda is negative, then minus lambda is positive, right? Where minus lambda is positive. Okay. But from ODE, my general solution to such an equation, think of the characteristic equation, the characteristic polynomial for this, is what? This would be x of x is some constant, say c1 e to the square root of minus lambda over x, if you like, plus c2 times e to the minus square root of minus lambda times x. Okay, for constants c1 and c2. Okay. All right. Now, what is it that you do here, right, in ODE? So in ODE, you'd say, well, I can actually determine these constants by imposing these initial conditions here, right? I can impose these initial conditions. Now, of course, we're thinking about this as we're thinking of these as boundary conditions because this x is a spatial variable we're thinking about. But here, this derivative is with respect to x, so whatever. These are initial conditions for our ODE, right? Well, let's impose these initial conditions. So first of all, if x of 0 is 0, so I have 0 is x of 0, but plugging in 0 here, this is e to the 0, e to the 0, so this is just c1 plus c1, or sorry, c1 plus c2, right? And then plugging in L here, I get that if x of L is 0, then c1 e to the minus, or here, no, sorry, square root of minus lambda L plus c2 e to the minus square root of minus lambda L is equal to 0. So I get this system. Okay. But then from the system, first of all, c1 is equal to minus c2. Okay, but if c1 is equal to minus c2, then what I get is that, say, like c1, right, is times e to the square root of minus lambda L minus e to the minus square root of lambda L, sorry, minus square root of lambda L, is equal to 0. And can this happen? Only way this can happen is if c1 is 0. Why? Because exponential function is 1 to 1, right? So exponential function is 1 to 1, so this quantity is not going to be equal. The only way that this is going to work is if c1 is 0. But if c1 is 0, that implies c2 is 0, since c1 is minus c2. Thus, it implies that these boundary conditions tell me that the only solution is identically 0, i.e., only solution is trivial. Okay. Thus, we have no negative eigenvalues here. What do we mean by that? Well, we want to write the eigenfunctions here. The problem is that the only eigenfunctions that can possibly result from these boundary conditions for this eigenvalue problem, in this case, are trivial. They're just 0, so that's no good. Okay. What about the case that lambda is equal to 0? So here's the case that lambda is equal to 0. Well, in this case, then x double prime is equal to 0, right? Remember, my eigenvalue problem, x double prime plus lambda x is equal to 0. If lambda is equal to 0, then x double prime has to be equal to 0. But this, I can just integrate this twice, right? This is like an explicit ODE, so I just integrate this twice to get that my x in this case would have to be like, you know, like c1x plus c2, right? But then imposing the initial conditions, right? So condition that x of 0 equals 0, which is equal to x of L, implies that c1 and c2 are both 0. So x is trivial again. Thus, lambda equals 0 is not an eigenvalue. Okay. Because if it was, then you know the resulting eigenfunctions would all be trivial, right? That's no good. That's not what I want. That's not going to give me a basis for anything. And so let's come to my last case here, right? Where lambda is positive. Okay. So here we have x double prime plus lambda x is equal to 0 here. Okay, recall from ODE. Well, let me write my initial conditions again. So from ODE, right? My characteristic polynomial is what? My characteristic polynomial, if you write it as like p of z, right? This would be z squared plus lambda, right? Where lambda is now positive. So this has imaginary roots, which means general solution. What happens when you're in second order linear ODE case, constant coefficients? You have two distinct complex roots. What does the general solution look like? You might recall that the general solution in this case looks like the following. So x of x is a cosine of square root of x, or sorry, square root of lambda times x plus b sine of square root of lambda times x. Okay, for constants a and b. And in this case, let's impose the initial condition here, right? So if 0 is equal to x of 0, plugging in 0 here, sine of 0 is 0, cosine of 0 is 1. So that's just a. So this implies that a is equal to 0. Okay. But what about x of L being 0? What does that mean? X of L being 0, what is x of L? That's, well, a is 0 here, so there is no cosine term. So this is b sine of square root of lambda L. And so I get a trig equation here, right? 0 is equal to the constant b times sine of square root of lambda L. So this leads to two possibilities, right? Either b is equal to 0, in which case I have a trivial solution, and so I'm not interested once again, so I don't want that to be the case, right? Or sine of square root of lambda times L is equal to 0. But the only time this works is if square root of lambda times L is an integer multiple of pi. An integer multiple of pi. So say n pi here, right, with n an integer. i.e., square root of lambda equals n pi over L, or lambda squared equals n squared, or sorry, not lambda squared, just lambda. Lambda is equal to n squared pi squared over L squared. So however you want to write this, you know you like that. Why? Right? So here are my eigenvalues. What are the corresponding eigenfunctions? Well, A is 0, B is some constant, right? I can choose that constant to be 1 if I like, because modifying an eigenfunction by multiplication via constant is not going to do anything. It still remains an eigenfunction, so I might as well choose this to be 1. And so in this case, my eigenvalues are lambda, which is n squared pi squared over L squared, where n is some integer, and the corresponding, I can index this with n if you like, and the corresponding eigenfunctions are sine of, so this is x of x, this is sine of square root of lambda x, but square root of lambda is n pi over L. Oh. Right. So square root of lambda sub n is n pi over L. That's another way of writing that. And oh my, right? Thus, by definition, my general Fourier series for phi on the interval 0 to L, here I'll write it like this, is what? Let's go back to my definition. My general Fourier series is this, where the coefficients are given by this formula. And so my general Fourier series is the sum from n equals 1 to infinity of a sub n times x sub n of x, which is the sum from n equals 1 to infinity of a sub n times sine of n pi x over L, where a sub n is what? Well, let's go back to our definition. It is the inner product of phi and x sub n over the inner product of x sub n with itself. So it is phi paired with x sub n over the inner product of x sub n with itself. But then this is the integral from a to b of phi of x times x sub n, which is sine of n pi x over L dx, divided by the integral from a to b of x sub n paired with itself, which is sine squared of n pi x over L dx. One of the orthogonality relations that you are, or the associated relations that you have to prove in the homework that's due tonight, is that this, of course, as we've seen previously, is L over 2. And so this is L over 2. And so all of this over L over 2, which is 2 over L times the integral. Sorry, this a to b is actually 0 to L. Let's be nice. There we go. So this is 2 over L times the integral from 0 to L of phi of x times sine of m pi x over L dx. Oh. So my general Fourier series is a series that looks like this. It's the infinite sum of a sub n sine of n pi x over L, where a sub n is determined by this formula, 2 over L times the integral from 0 to L of phi of x sine of n pi x over L dx. What is that? Right? This is just the Fourier sine series from earlier. Okay. So if we had never, ever defined the Fourier series before in your entire life, then following this process would have led you here anyway, right? So that is the point. The point is that in this case, the Dirichlet boundary conditions led me exactly here to the Fourier sine series. Okay. All right. What about the periodic case? All right. What about the rest of the cases? In fact, let's go ahead here and just go ahead and write them out. So the full list. Okay, the full list. All right, you can find these actually on pages. What should I? This is on pages 460 to 462. If you're using the e-copy. Okay. And so similarly, we can do this for the Neumann case. We can do it for periodic boundary condition, which causes us to have to use a slightly different orthogonality relation, which you should recognize. There. All right. Hey, have you recognized this? This is also homework due tonight, right? So that relationship that can be shown by direct integration can also be shown as one of the other orthogonality relationships. Now, not just between sine n and sine m, but also between sine n and cosine n. Okay. I don't know why my thing's having a problem with focus. There we go. So what is this full list? What about Dirichlet boundary conditions? So Fourier series. Fourier series for Dirichlet boundary conditions. So we have an interval 0 to L. We have boundary conditions x of 0 equals 0 equals x of L. So these are homogeneous Dirichlet boundary conditions. The eigenfunctions and eigenvalues are as follows. So as we just saw, the eigenfunctions are sine of n pi x over L with our eigenvalues lambda sub n being n squared pi squared over L squared. And n here is 1, 2, 3, and so on, right? All the positive integers. The corresponding Fourier series is the sum from n equals 1 to infinity of a sub n times the eigenfunction sign n pi x over L, okay, where a sub n, of course, is defined by our formula, so this is the inner product of phi with x sub n over the inner product of x sub n with itself. This is 2 over L times the integral from 0 to L, phi of x times the eigenfunction sign of m pi x over L dx. And again, n is 1, 2, 3, so on. It's positive integers. This is the Fourier sine series, i.e. the Fourier sine series. Of phi on 0 to L. Okay. What about for Neumann boundary conditions? You've probably already guessed this. So I again have interval 0 to L. I have homogeneous Neumann conditions, which tells me that the derivative now of x at the endpoints is 0. This gives eigenfunctions and eigenvalues as follows. The eigenfunctions, I'm sure someone has already guessed what they are. Cosine of n pi x over L with my eigenvalues, lambda sub n, again being n squared pi squared over L squared, with n being positive integer. Okay, the corresponding Fourier series is, again, this is a naught over 2 plus, so these are indexed. Sorry, I actually screwed this up. This indexing, I should have been careful to note here that 0 is now an eigenvalue. So this indexing starts at 0 to reflect that. So I have a constant term here pulled out, a naught over 2 here, plus sum from n equals 1 to infinity of a sub n cosine of n pi x over L, where a sub n is again defined to be the inner product of phi with x sub n over the inner product of x sub n with itself, which is 2 over L times the integral from 0 to L of phi of x times cosine of n pi x over L, again indexed starting at 0. Which, of course, is our Fourier cosine series. So what is the tale here? What's the story? Well, the story here is that we began defining Fourier sine cosine full Fourier series and saw what properties they had, what they were doing, right? Kind of, just out of nowhere, right? We just decided to consider those things. And now we see that we are happy that the eigenfunctions that we saw to begin with turn out to be exactly those nice things, these Fourier series that we were dealing with. Now, It still remains to be seen what this has to do with PDEs or what we're doing here, but at least now we know these eigenfunctions solve these special, right, these special ODEs, these eigenvalue problems. And that is really the kicker, is that they solve these eigenvalue problems. So, and you'll see why that's so important here in just a little bit. Okay, let's keep going here. So again, my full list here is as follows. I have one more for periodic. So what about periodic BCs? Okay, so now we have an interval minus L to L. We have periodic conditions. So x of minus L is equal to x of L, and x prime of minus L is equal to x prime of L. So the values of x and its derivatives are equal or at its first derivative is equal at the endpoints. So these give rise to eigenfunctions. We actually get two distinct eigenfunctions associated to each eigenvalue. So we'll call these, instead of just x sub n, because that would be confusing, we'll call these y sub n of x. So this is cosine of n pi x over L. And those are indexed starting at 0. And the second eigenfunction associated to lambda sub n, that is sine of n pi x over L. And those are indexed starting at 1. Okay. Corresponding to eigenvalues, lambda sub n, which are, as usual, given as n squared pi squared over L squared, indexed starting at 0 here, because 0 is an eigenvalue. Okay. The corresponding Fourier series is 1/2 a naught plus the sum from n equals 1 to infinity of a sub n cosine of n pi x over L plus b sub n sine of n pi x over L, where a sub n is, after we do, so this would be phi paired with y sub n over y sub n paired with itself, which is 1 over L times the integral from minus L to L of phi of x cosine of n pi x over L dx. And that's for 0, 1, and so on. And b sub n is phi paired with z sub n over z sub n paired with itself, which turns out to be 1 over L times the integral from minus L to L phi of x sine of n pi x over L dx, where n starts at 1, 2, and so on. What is this? Well, this is the full Fourier series of phi. So that's the full Fourier series of phi. Now, this list in the textbook includes one more, which is a mixed boundary condition. You can have a look at that if you want to, but these are the three most important ones. Okay. Now, the ultimate miracle. every reasonable function phi on, say, some a to b, right, can be written as such infinite linear combinations of those eigenfunctions. So sine and cosine, right? Okay. So what is this? What's another way of recasting this? It's to say that these eigenfunctions we found in the terminology of linear algebra, these span the space of reasonable functions. Right? Now, what do we mean by reasonable? If you insist, we'll say, without making too many extra assumptions here, reasonable. An example of that would be, so for instance, L2 is fine. So an L2 function, recall a function, right? So f is in L2 on some domain omega. What does that mean? That means that like the integral over omega of f squared, right, is finite. So these are called square integrable functions, if you like, L2 functions. This is enough. I believe when Fourier originally made this claim, he claimed that it was true for any function. I think that's the case, and so like mathematicians at the time were absurdly skeptical that that was the case. Although and that it's not true that this all works out and everything is sunshine for every single function. But for a ridiculously huge class of functions, this is true, can be made to work, and it's pretty amazing. It truly is a miracle, because this whole time we had to make these assumptions that that our function could in fact be written, could be expressed as this linear combination, when there's absolutely no reason at all, right, a priori, why that would be the case. But indeed, it is the case for reasonable functions. And so this process, right, that we've done here can be used for basically any reasonable phi you can cook up. And so what do you think those reasonable phis are going to be? Where are those going to come from for us in PDE world? Those functions are going to be my, say, initial data, right? Are going to be my initial data, for instance, right? In the case of, say, the heat equation or the wave equation. So that's this is truly the thing that ties it all together. So what this really says is, so this really is a statement, or rather a group of statements, right, about convergence that we're not going to get into. So we're not going to get into any of those. If you want to see the details, roughly you can look at, maybe I should just estimate here. So like basically like 463 to 474. So like pages 463 to 474 will get you there. But also, we have nice things like term-by-term differentiation. We're not going to justify that. We're just going to give it the thumbs up. We have term-by-term differentiation, term-by-term integration if we really like. So you might recall previous notions when you first dealt with, say, like Taylor series, or you first dealt with power series in general, term-by-term differentiation of these things. You may recall, like I said, from like a Calc 2 class or whatever here, all of this stuff can be smoothed out to work very, very nicely under the right assumptions, so we're not going to worry too much about it. There's even more convergence stuff that happens after, so basically the rest of chapter 11 in the textbook covers this kind of stuff. We're not going to get too bogged down in the weeds, though. Okay. And so now we have finally done it. We've finally gotten to a point where we can start applying this stuff to PDEs. So let's do it. Okay. So the big question that we haven't answered yet. Right, what does any of this have to do with PDEs? I have, of course, mentioned the phrase separation of variables. You've encountered separation of variables in another context, right? In fact, separable ODEs, right, were called separable because the equations could be separated into an equation involving x, a term involving x and term involving t. You could think of your function as being separated in terms of the variables like that. So this is an example of that. But here this is slightly different. Okay, this is going to be slightly different how we do this. Well, it's going to be vastly different in terms of actually carrying this out. This is going to have a lot of steps. It's going to be a little overwhelming at first, but that overwhelmingness is going to be overcome by just doing a bunch of examples. So the answer, of course, is the separation of variables algorithm requires it. Requires all of the Fourier series machinery. In fact, without getting too much into the history, I believe that Fourier's original discovery of this stuff had to do with his attempts to solve the heat equation. So this arose directly out of those considerations. So in fact, like Fourier series themselves came into being basically from his attempts to deal with the heat equation. So okay. So what does this have to do with PDEs? It's the separation of variables algorithm. Let's see a very, very quick example here. So I mentioned this thing previously. So I'm gonna just write this as u sub t equals u sub xx. Okay. Now I'm not going to give any boundary conditions or anything. I'm just going to write it like this. Suppose that suppose I assume I did this at the end of lecture yesterday. Let's make a huge assumption, of course. Let's make a gigantic assumption that the solutions that I seek are separated. So, right, this is a separated solution. And of course, it's separated in the sense that the variables x and t have been separated, right? Hence separation of variables. They've been separated into a term where only x, this term big X only depends on x, and this term big T only depends on t. Okay. And so, how does this help me? So then yesterday at the end of lecture, I did this computation here, right? So u sub t is going to be, well, this t partial now is only going to fall on the t, and since t is only a function of t, this is going to be a full derivative of big T. So this is going to be x of, sorry, not x of t, x of x times t prime of t, right? Okay. Then this now, so now what? Well, okay, u sub x, I can go ahead and say these two partials only hit the x function, so this is x double prime of x times t of t. But the fact that these satisfy the heat equation tell me that x of x times t prime of t is equal to x double prime of x times t of t. So what I'm going to do now is divide both sides by, so I'm going to divide both sides by t and x, which leads me to the following expressions. I have t prime of t over t of t is equal to x double prime of x over x. For convention's sake, I am going to introduce a minus sign here. If this is true, then certainly this is true, right? So in yesterday's hint, I left it a little bit unclear as to what was going on here, right? If you try to do some manipulations, we're kind of lost in the sauce here. But what's the reason for doing this? Again, it's to separate these into variables, right? So the left-hand side, I've separated the variables so that the left-hand side only depends on t, the right-hand side only depends on x. But let's think about what this means. The left-hand side only depends on t, the right-hand side only depends on x. How could that be, right? Unless, in fact, these quantities are constant, right? If these two quantities are equal, right, for all t and x here, right, because the left-hand side is purely a function of t and the right-hand side is purely a function of x, these two quantities must be equal to some constant that I'll call lambda. But if that's the case, these two equations, considered separately, split into two ODEs. One is this one. The other is this one. Oh, but wait. That's two ODEs, one of which is something that I've seen very recently. Oh. Oh. So, solving those two ODEs is somehow going to yield me a solution to my heat equation. Well, what's the idea now? If I were to impose, say, boundary conditions, right? So, let's say u of 0t is 0, and so is u of lt. These are now Dirichlet boundary conditions. Those boundary conditions, since they're conditions in the x, fall onto this ODE. They become boundary conditions for this eigenvalue problem. Well, guess what? I can then solve that eigenvalue problem with my canned Fourier series. What is the phi that I'm looking for? It's the initial data. Right. Now, we're going to forget this for a second. We're going to do this in complete generality here. And then we're going to do one example for today, and that's all we're going to have time for. And then we'll stop until tomorrow's lecture. But let me get some more paper. There we go. Okay. So, what does this look like? Well, what is the separation of variables algorithm? So here it is. Okay. We look, so first step, we look for a separated solution for the PDE to the PDE and boundary conditions of the form u of xt is equal to x of x and t of t. That's the first step in separation of variables, right? We then note that the separated solutions reduces to solving eigenvalue problems. Eigenvalue problems for x and t with the same eigenvalue. That's step one. And we'll see how that works. And two, the BCs carry over to the eigenvalue problem involving x. We solve this as we previously did in all cases. To remind you, we had a list, right? Here's the Dirichlet case. Here's the Neumann case. And here's the periodic case, where this was just the full Fourier series. Okay. Okay. So next, after we've solved the boundary or the eigenvalue problem for x, we now have to solve the eigenvalue problem for t for the eigenvalue lambda n found in the previous step. We now solve the eigenproblem for t using the lambda n eigenvalues found in the previous step. Thus, we arrive at infinitely many separated solutions. That look like this. We'll call them u sub n of xt that look like a product of the corresponding eigenfunctions. I keep writing x of t. This is x sub n of x and t sub n of t. Yep. Okay. Okay, so these are separated solutions to the PDE and the boundary condition. Okay. We note that any finite linear combination of these is also a solution. This is the superposition principle for linear PDEs, right? So we then consider, instead of a finite sum, we then consider an infinite sum of the form sum from n equals 1 to infinity of a sub n times x sub n of x, t sub n of t, with coefficients a sub n. And 5, solving the problem means choosing a sub n that force this to work. What a sub n do we choose? A sub n equals the general Fourier coefficients work. So if we choose these coefficients in a way that these are just the general Fourier series coefficients that we have been writing out, then this process works and we are done. And so that our completely figured out solution, right, our complete answer to our solution to the PDE plus boundary condition is given by this thing. Right, this thing that I've boxed here. Draw a red line around it. Okay. So one way to think about this is that steps 1 through 3 are finding eigenvalues, eigenfunctions. And steps 4 and 5 are finding the coefficients. But other than that, everything in this is, this is exactly how it works. So I find the eigenfunctions, eigenvalues here. I write out this as my solution. I'm done if I can compute these coefficients, but I can compute these coefficients because they are Fourier series coefficients that I've computed previously. Okay. Now, I think rather than trying to fit this in because it would probably take me another 10, 15 minutes here, even though it would be really, really good to throw in an example here, I think better is tomorrow, first thing, we will do examples of this. And we will basically be doing examples of this over and over again pretty much for the rest of the course. So pretty much the rest of the course will be nothing but examples of separation of variables. So we got plenty of time to do plenty of examples. So I think I'm going to end it here and proceed with our absolute kind of grind fest of examples tomorrow. So tomorrow is when we'll start doing that. Anyway, so I will see you all tomorrow.